Okay, in the last video, we were looking at the consequences of time dilation, length contraction, and one of the issues that I glossed over at the time was what we called the twins paradox. So let me go ahead and state the twins paradox here. So let's imagine that we have two twins, both born on Earth. O, we'll say, is a professional archer and has a very long and successful career, but O prime decides to become an astronaut. O prime joins the expedition that takes them from Earth over to the star Bob. Now, the spaceship that they're traveling goes at 0.9 the speed of light. The star Bob is 10 light years away from our sun. But they discover when they get to Bob, that the Bobians do not take very kindly at all to other civilizations visiting their star, and they very forcefully make their displeasure known. So the astronaut mission just immediately turns right around and starts heading right back to Earth, again at 0.9 C. So here's the issue. Each of them is going to swear that the other one is the one moving. Each of them is going to swear that the other person's clock is running slow. So when they get back, who's younger, or are they the same age? Think about that for a second, come up with your idea on that, and then we'll follow up. Okay, it turns out that the astronaut is younger. And you might say, but wait a minute, you just said they're both swearing the other person's moving, they're both swearing the other person's clock is running slow. How could it possibly be that the astronaut ended up being younger? And I'm going to argue if you look at points A, B, and C in the journey. At point A, the astronaut had to accelerate from 0 to 0.9 C. At point B, they had to accelerate from going 0.9 C to the right to 0.9 C to the left. Now at point C, they had to accelerate from 0.9 C down to 0. At those three spots, O prime is not an inertial observer. Remember, to be an inertial observer, you have to be moving at a constant velocity. So these three accelerations break the symmetry and will allow us to conclude that O prime is younger. Now, wait a minute, you might say. This trip out to the star Bob is going to take quite a while. The distance is 10 light years. Remember, light is light years the distance light can travel in 1 year. So another way we could write the speed of light is to say that it's 1 light year per year. So doing the math on that, it should take 11.1 years, according to the Archer, for the astronaut to make it out to Bob, and so 22.2 years for a return trip, for the round trip. That's an awful long time. And especially if we can imagine some sort of technology that keeps the astronaut from being smashed into a pancake, we could imagine that the accelerations at points A, B, and C were very short compared to those 22.2 years. Isn't that enough to get us out of Dodge? That's seemingly a compelling argument, but there's still another way that you can argue that the symmetry is broken. So once again, I want you to think about that, pause the video, and we'll get back. Okay, so it turns out that you can also just say, well, hey, even if we wish the accelerations away down to infinitesimalness, the astronaut was in two different reference frames. First, they were going at 0.9 C to the right, then they were going at 0.9 C to the left. That's two different reference frames. Their velocity was different at those two times. Their speed was the same, but the velocity was different. So that's still enough to break the symmetry. So I went ahead and did some of the math on that. So first off, we can say, all right, the astronaut, let's go ahead and calculate the distance between the sun and the star Bob according to the astronaut. If you go ahead and do that, dividing through by gamma, you will get that the astronaut says that the dilated length is only 4.37 light years. Just keep in mind, the astronaut is swearing that they're stationary and the sun and Bob are both moving either toward or away from them, depending which phase of travel we're talking about. Okay. Similarly, we can work out how much time the astronaut would say would elapse. So for the astronaut, this is a proper time because they're not moving. And so it would be 4.39 light years, and then we can divide through by our 0.9 light years per year speed to get that the proper time elapsed between the events of star leaves astronaut and Bob arrives at astronaut works out to be a grand total of 4.85 years. Okay. And by the same token, we already worked out, and you can check that the factor of gamma works for this, that the dilated time between these two events was 11.1 years. Okay. So let's think about how we can demonstrate that indeed O prime will be younger than O. Probably the easiest way to think about this is to say that O is going to send out on their mutual birthday back on Earth, will send out a happy birthday message every year. Okay. O prime is going to say, when we do the time dilation on that, is going to say that the messages were sent every 2.29 years, but because they're running away from the message, or more to the point, they'd say that the sun is moving away from them and there's extra distance to be traveled between messages, it'll work out that O prime will receive a message every 4.35 years. So grand total on the outbound leg, we will receive, to an absurd number of decimal places, 1.115 birthday messages. On the return leg, O prime will be running into the messages, or what O prime would say is that the sun is moving so much closer that the spacing between the messages is much closer. And so it turned out that there he would be running into a message every 0.229 years, and we receive a grand total of 21.188 messages per year. Add them up, 22.2 messages. So O prime definitely agrees that O aged 22.2 years because O sent out 22.2 messages in that time. But according to O prime, the whole trip took 2 times 4.85 years, which is 9.7 years. And so both of them would agree that O prime is younger than O now. Now this seems this can seem a little daunting, but go and work through it a couple times, you'll be okay. But we can leverage this to come up with something more useful. So in a certain sense, we've tested this all the time. And this would be the relativistic Doppler shift. So the idea is going to go like this. Let's say we have some observer S sees a light source. That is, we'll just say it's emitting light out spherically. So it's heading out at the speed of light uniformly in all directions. So now let's say that you are some observer S prime who is seeing S approach you. Okay, so at time 0, S was located here, and then at time 1, S is located over here. So we'll have had a wavefront propagate out like that, and here it would have been centered around that, because S prime is going to say it just goes uniformly around. That's supposed to be a circle centered around O, sorry. Let me try to draw it a little better. Okay, no better. Sorry about that. But it turns out to be the exact same argument. The birthday messages are when you receive the crests from the light wave. So here we can say that the wavelength is lambda, and here we can say that the wavelength is lambda prime. This distance here would be v times the period of the waves, the dilated period of the waves. I'm calling that t prime at the moment. Okay, so we can work out that lambda prime would be c t prime minus v t prime, and we know that f prime lambda prime would have to equal c. That's still true. So we can say that the frequency is c over lambda prime is c over ct prime minus vt prime. Okay, but we can time dilate those t's, right? So we can say that the frequency we observe would be equal to 1 over c, we can pull out a gamma, right? And then this just becomes, oops, my bad. This becomes gamma ct minus vt. So we can say that that is 1 over gamma t c minus v. All right. And we can again say that t is 1 over the frequency. So we can get rid of the t there if we put an f up there. Once you rearrange things a bit, so I'll skip some tedious algebra, but once you rearrange things a bit, the result you end up with is that the frequency that gets observed is the square root of 1 plus or minus v over c over the square root of 1 minus or plus v over c times the frequency of the source. Now, you use the upper signs if you're approaching, So this plus and that minus, and use the lower signs if you're receding. Notice that this behaves a little differently from when we did the Doppler effect for sound. The Doppler effect for sound, there were 4 possible combinations of plus and minus signs in the general relationship. Here there's only 2. And this is again because with the Doppler effect for sound, there is a preferred observer. The preferred observer is one who's stationary with the air. So they get to say who's moving right and who's moving left with respect to the air. Here, with light, there is no preferred observer. And so all you can say is, are you approaching each other or are you receding from each other? There is no observer who can definitively say who's moving which way. So that's why we resort to a choice of 2 signs. All right, let me just end this particular video with one fun application of this. And this is how we detect most extrasolar planets. So let's say there's a star and you have some planet orbiting the star. Now, if you remember in your mechanics class, you went ahead and we calculated that there was a definite period based on the radius and the mass of the star. What you may or may not have learned, though, is that the star also has to orbit as well, and they orbit about their common center of mass. Now, in say the case of our own star, the Sun, if I remember correctly, this common center of mass between the Sun and Jupiter, our most massive planet, sits under the surface of the Sun. So we're not talking a very big orbit. It's orbiting around, a lot of these stars are orbiting around a point that's located within themselves. But the point is, the star is orbiting around this common center of mass with the same period as the planet. So now let's say we're out over here looking at it with our telescope or whatever. When the star is heading toward us, the upper signs come into play. The observed frequency is higher, which means the observed wavelength is shorter, which means the light is shifted to the blue. When it's heading away from us, the lower signs come into play. This will make the observed frequency lower, meaning the observed wavelength is longer, meaning that the spectral lines of the star get shifted to the red. And so if you take a lot of spectra of the star over time, you'll see this, you'll see all the spectral lines just kind of oscillate a little bit back and forth between red and blue, a bit towards the blue or a bit towards the red of its average position. From that, we can deduce that there must be a planet tugging the star around, and we can figure out the we can figure out the period of the orbit. From other astronomical considerations, again having to do with the spectrum of the star, we can pretty accurately deduce the mass of the star. Because you know the mass of the star, we can reverse engineer this to figure out a bound on what the mass of the planet must be. There is a technical issue having to do with the fact that the planet's orbit may be inclined with respect to the line that connects us and the star. So usually all you can say is its minimum mass is this, although there are times where you can dial it down a little better than that. Alrighty, catch you in the next one.